overview about baby peer-to-peer. So peer-to-peer is a hybrid peer-to-peer file share system. So what's the hybrid mean? So we have a decentralized peer-to-peer network for file sharing, and we also have a centralized database for the storing file metadata. And between those two layers, there is orchestration layers. That means we have that will handle the request between the hybrid layer and the centralized layer. So here's the architecture of our app. So as I mentioned before, here's the decentralized P2P network, and here is the centralized DB database network. And we will implement the data injection in this layer. And between the front end and back end layer, there's a reverse proxy here to handle the request between the front end and back end. Yes. So we have three major components in our app. So we have peer app, reverse proxy, and the central registry. So now we have let our my teammate Wasif to introduce the peer app.
So as Ken mentioned, we have a reverse proxy that routes the request to the central registry, which has the database, so either the DB manager that processes these requests and then executes them on the SQL database. Moving on to the peer app, we have the Bootstrap node. Now this is a dedicated Bootstrap node that runs separately on a Google Cloud instance and runs with a static IP, so always any peers can always connect to it. And those connect to it to actually register themselves and be a part of the P2P network. So when a peer first initially starts, it attempts to connect to the Bootstrap node and registers itself in the cadet via DHT. And periodically, it broadcasts its presence in the DHT so other peers can discover it as well. And the DHT obviously maintains the routing table of the peers. Next slide, please. Let's talk about the file search and retrieval. The peer searching for a file first queries the reverse proxy by file name and gets relevant CIDs. Imagine this is like manifest.json file hashes, but a modified version of that. So once the manifest CID is obtained, it performs a DHT lookup to find which peer is providing that manifest.json file, and then connects to it directly using the P2P streams and downloads it. Once the manifest.json file has been downloaded, it opens it up and looks at the chunk CIDs that are stored in it, and does the same process over again for each of these chunks to retrieve all the chunks from different peers, and then connect to these peers through the P2P streams, download all the chunks before it becomes to the file locally. Next. Now, is the file a virus? The way we do this is by immediate file integrity verification. So after receiving the file, peer generates a CID from the downloaded file, compares the CID with the original file to verify if verify the file's integrity, and if the CID is matched, then it's authentic and unmodified. We do this for the manifest.json file, and after that data has been downloaded, we do it for each of the chunks. And each file is chunked, like we mentioned before, into pieces and distributed across the peer-to-peer network. And this ensures file transfer can still carry on even if the original file provider goes off. So we designed this to be the least centralized way possible, and the data is being the only centralized point where our manifest.cid is. Next slide, please. So these are the two screenshots of our peer app. We have the download, upload, and progress tabs, and listed are some of the most important files you want to share with your friends and colleagues. We used 559 final exam PDF to share, but we still failed it. Next, I'll give it to you.
So reverse proxy. So our reverse proxy is this server with a static IP that connects the peer nodes to the database manager clusters. So as a file sharing system, we provide two operations, file upload and file download. So file upload are those post requests that will be forwarded by our reverse proxy only to the leader node, whereas for the file download, which are GET requests, will be forwarded to all database manager nodes in a round-robin manner. At the same time, our reverse proxy keeps track of the address of the current leader in memory, and then whenever a new leader is being elected for whatever the reason, it will inform our reverse proxy on the IP address of the new leader, so that in the future, all the write requests can be rerouted to the correct database manager node. Currently, reverse proxy is relatively the weak point in our system due to the single point failure. However, this can be easily mitigated by deploying our reverse proxy with multiple instances to any cloud platform.
Okay, so the last part of our system is called central registry. It's a cluster of database managers. It consists of an HTTP server written in Go and a Postgres database. Database just has one table which has file name, content ID, file size, and write request, it appears to the reverse proxy, it stores that in its own database. Well, actually, first it propagates all the rights to the follower nodes, and if it gets majority acknowledgement, then it sorts it to itself and sends the successful response back to the client. So for fault tolerance, the followers periodically check that the leader is alive for the heartbeat monitor, and if the leader is discovered to be dead, then an election is triggered. And if the follower dies, they're automatically skipped over by the reverse proxy, and it does over, which makes the access transparency high because the user won't know if any of the measures failed unless half of them failed.
Alright, so for our leader election, we went with sort of a fully linked algorithm. We selected that just for ease of implementation and had offered a lot of robustness to our system. Every manager, database manager will store the IP address, port number, and the index of all the database managers that are available on the network. And that way our algorithm can guarantee that the current leader will always be the manager with the highest logical timestamp that it keeps in its database. Ties are broken. In the event that there's during an election that there's a tie, the ties are broken with the manager that contains the lowest index. And our election trigger mechanism is if heartbeat failure for any of the managers or any managers coming online either through recovery or initialization. So quickly just through our election process here, so if the manager notices that there's or triggers an election, it sends an election message to all the managers that are on the network. No response is received from anybody else, then it automatically elects itself as the leader. Responses are received, then the manager with the highest timestamp in this database is elected to be the leader, and the leader message is sent out to all the other managers on the network. The manager waiting for a leader message, if there's a manager waiting for a leader message and it doesn't receive one before a timeout, it will automatically trigger an election. Managers, when they receive the leader announcement, it sets out leader address, it's received in its message, and then it starts its heartbeat monitor. The reverse proxy receives that same leader message, it will update its leader index and starts driving the right request traffic to that node. With the way that we've set it up, there is a possibility that we've got simultaneous elections going on. So if that does, and more than happens, and more than one leader is elected, the proxy only updates with a single address. And then once the leader receives a right propagation from another leader, for instance, it will trigger an election in that case. Okay, we'll go quickly through our consistency model here. When the leader receives a right request from the user, that right request is immediately propagated to all the other followers on the follower managers. When a follower receives that right request, they commit it to their own database, they increment their timestamp, and then they send an acknowledgement back to the leader manager.